Okay, so this is our week in this. We can see that we've got a warm up. We're going to work on rotation 5. That's practice problems based on the information that we already have. Some of them are sort of challenging, so we're going to work through most of that together. Then we're going to get into new material towards the last third of class. So don't sleep on the class because you're going to miss out on angular momentum, which is going to be towards the end of class. We're going to start with this, the time down the ramp. Let me zoom this in just a little bit, that you have the opportunity to take a look at this. I want you to get an idea of which one's going to be first down the ramp, A, B, C, or D. Take a second to look at this. In the information, it does give you the moment of inertia or rotational inertia for each of the 3 different types of objects, 2 solid spheres, 1 hollow sphere, and 1 hoop or ring, I guess. Look at that, see what you come up with. First to the bottom fastest. All right, so what do we think? We can put it in the chat. We can say it out loud. What do you think is going to be the fastest? I already have 1 vote for C. What else do we have? What do we think? All right, so someone put solid sphere in the chat. There's 2 solid spheres there. All right, I see A, I see A, I have C, I see D. No one's going for B that I can see. Let's see. I don't see any B's. Oh, now I've got a B vote. All right, what about out loud? Anybody want to be big and bold and say things out loud? What do we have? What do we think?
I think letter A.
Why do you think letter A?
Because it has the lowest moment of inertia, therefore it has the lowest resistance to rotational motion. So it will be first to reach the.
Okay. We did end our last class by saying the object with the largest rotational inertia has the largest rotational kinetic energy and would have the less amount of translational or linear kinetic energy. So that falls in line. So then that would mean that the solid spheres would probably be first, fastest, then the hollow sphere, then the hoop. But what about between A and C then? Which one's faster?
A.
All right, I've got an A. Oh, let's see. All right, I've got a perfect answer in the chat, but I'm going to hold off on saying it out loud until I get some more votes. Let me hear some more. Yeah, it is you. So let me hear some things that are audible. Let me hear some things. Between A and C, how are we going to differentiate? Okay, let me give it away a little bit more. Do we need to differentiate between A and C?
Yes, because the mass is different.
Okay. Does the mass matter?
Yes.
Would I ask if the mass mattered? All right, I'm gonna do a little bit of math, okay, on the equations on this page. I've got it to where I can type right on the page. And what I was commenting on, I get to see the direct messages that you can't see, but I'm going to try to go back to this particular comments. Aren't they same since masses cancel out? Yes. And then someone else said masses cancel out. Someone else said A and C from the beginning. And let's just look at it, okay? So when these objects are at the starting line, they're not moving yet, but they have height. Okay, so they've got gravitational potential. So I've got UG at the beginning. And then as they rotate and go towards the bottom, they're going to sacrifice that gravitational potential, the height, and they're going to convert that into both kinetic energy, because they're moving from the top, they're moving from right to left. So they have some displacement, they've got some linear velocity, but they're rotating. So they also have, K rot, which is our rotational kinetic energy. I just affectionately call it K rot, okay? Now, if UG is mgh, and then kinetic energy is 1/2 mv squared, and then K rot, okay, let me do this off to the side in a different color. So K rot, that is essentially what, 1/2 times m No, it's 1/2 I. Oh, come on, talk to me. 1/2 IR squared? No, that's not right. 1/2 I, what is it? Omega squared? Right, I'm going to keep you on your toes. 1/2 I omega squared. And then what is essentially I? I is the rotational inertia. In this case, for the solid spheres, that would be 2/5. Isn't that what they tell us? Okay, so then we can take this part right here and we can rename this 2/5 mr squared. And we can even say it's V over R squared, right? So then when I go back to my original formula, when I put in K rot, I can say that it is 1/2 times 2/5, which would that be 2/10 or basically 1/5? 1/5. If I do the math wrong, you have to speak up. M V squared. Wouldn't that be kind of the abbreviation? I'm basically taking the information and breaking apart and converting it. Doesn't that then allow me to cancel the masses? So mass doesn't matter. When we're looking at this, mass does not matter because it cancels out. So that means A and C are going to reach the bottom at the same time. See, there is rotational because of friction. Yes. The only way that you're going to get that rotation is from friction. In order to rotate, you need a force that causes rotation. Now, we talked about torque. Actually, I can just stop the share because it's really weird to stare at that when I could be staring at all you guys. In order to get rotation, we have to have a force that causes rotation. And we talked about torque. Torque is that force that causes something to rotate. Now, in this case, there's no force coming in at an angle kind of thing that we think of or we can see physically. But friction itself, as an object is rotating, friction keeps it from sliding, right? So that friction is a force that is opposing motion, causing that rotation. So yes, you absolutely need friction in order to rotate. If these spheres and did they call it a hoop or something? If all of that was sitting on a block of ice, frictionless ice, they would just simply slide right down. They need that friction to cause the rotation, to push on the bottom, causing it to rotate so that it doesn't slide. And so, yeah, it's got to come from somewhere. Okay, so I think I've caught up most of what was in the chat. If I missed something, put it back in there. I'm going to see it again. It's not personal. Also, I run 2 devices, and sometimes it'll throw the chat in the device I don't look at the chat on. So if I'm not answering you, it's not because I'm being mean. It's just, it's not popping up on my Mac that I'm primarily using. All right, so we've got that. Let's take a look at what else we have for today. That was our warm up. Sorry, I got to rearrange in order to get to our actual stuff. So here is our practice. All right, let's do this. I'll do the first one just to kind of get us woken up from our lunch coma, and we can kind of get warmed up to actually doing physics today. I'll do number 1. That'll get you set up for number 2. You guys can work on number 2. 3 and 4 don't exist. I don't know what happened to 3 or 4, but they're gone. And then we'll do 5 together and the first half of 6 together. All right, sort of fair. Let's get it started. All right, we have a wheel that has a moment of inertia of 500 kilogram meters squared. So let me get my drawing tool out. All right, they said it's a wheel. So a wheel, think of like a tire. It's like a hoop or a ring. So couldn't we say that I equals mr squared? I don't know if I need it. I'm just going to put it off to the side. Then they tell me the moment of inertia or the rotational inertia. So they say I equals 500. Okay. How much rotational kinetic energy? So it's asking for K rot. Will it have if the rotating at 25 radians per second? Radians per second is my angular speed or velocity, angular velocity, either one. I don't really, it doesn't matter here. So I've got omega is 25 radians per second. All right. So if I know that K rot is equal to 1/2 times I times omega squared. That's just a formula straight off the formula chart. So K rot is 1/2 I times omega squared. Then that's going to equal what's 1/2 times I is 500. times omega squared, which would be 25 squared. I feel like that's just way too easy, but it kind of is. 156,250 joules. And then I can just put the K rot back in here. I just dropped it because I was being lazy. But I've got an answer. Not bad at all. By writing my known components, my given information in the margin over on the left side, I'm able to grab the things I need and solve. So let's look at B. What is its angular velocity? So I'm looking for a new omega when it has that much kinetic energy. So I've got K rot is equal to 2.25 times 10 to the 5th joules. Okay, well, I'm gonna start with the same formula. K rot is equal to 1/2 I omega squared. Pretty sure that's the formula. I need to rearrange it to solve for omega. So I'm gonna multiply both sides by 2 to get rid of the half. I'm gonna divide by my my rotational inertia or moment of inertia, and then square root. That just kind of moves things around. So I would say it's like, and I'm gonna drop the rot part because it's annoying. It makes me write too much. So what if I just said 2 times the kinetic divided by I equals omega squared, and then draw an arrow, bring myself over here, the square root of 2K over I equals omega. Does that work? I hope so. It should be sort of right. In this case, if I start plugging numbers in, I'd have the square root of 2 times 2.25 times 10 to the 5th divided by my I. So what is I here? I is still 500. That equals omega. Bring it up over there. When I did the math for this one, I got 30 radians per second. By saying 2 times the quantity, 2.25 times 10 to the 5th power, divided by 500 equals square root that answer, I got 30. Not too bad. I mean, this is really just kind of some algebra when you're just identifying variables and plugging things in. Not bad at all. All right, I want you guys to do number 2, A, B, and C. I'm just going to scroll this up out of view. Don't worry, it'll be in the recording. It's all there. Let's look at 2, A, B, C, D. I'm going to give you a minute head start. I want you to work on this one to the best of your ability. Having the experience doing the question does help. So read through, write your given, calculate A, B, C, D. You got a minute head start. In my margin, I've written my given. I've got the rotational inertia equals mr squared. I have the that's based on it being a wheel. I've got my mass as 0.5 kilograms. My radius is 0.25 meters, and my tangential velocity or my linear velocity as being 10 meters per second. I know that that was linear velocity because the units they gave me, meters per second. If it was in radians per second, that would be my angular velocity. So knowing the units really helps identify my variables. Question A says calculate the angular velocity of the wheel. So it's looking for omega. So I've written omega question mark. So just to know what I'm looking for, it keeps me centered and on the right track. I have a formula that says that omega is equal to velocity divided by radius. So I've written that formula down. Now I'm gonna go ahead and plug it in. Velocity is 10. Radius is 0.25. Put that into a calculator. 10 divided by 0.25. What do we get, like 40? 40 radians per second. 2b, calculate the translational kinetic energy of the wheel. Translational kinetic energy is our linear kinetic energy. It's the 1/2 mv squared. So I've said K is equal to question mark. That's what I'm looking for. The formula I would use is 1/2 mv squared. If I come in then and I would have K is equal to 1/2 times the mass of 0.5 times the velocity 10 squared. Half times a half times 10 squared. When I calculated that, I got 25 joules. For C, calculate the rotational kinetic energy of the wheel. So I'm looking for my rotational kinetic energy, my K rod, which is equal to 1/2 times rotational inertia times angular velocity, or omega squared. So that would be equal to 1/2 times I. Didn't we say I was 500? Or no, that was for the previous question. I don't have I yet. Okay, well, I equals mr squared. So I've got that part. I can just plug in m times r squared times, since I've got an r squared, I should probably convert the omega to v over r squared so I can get rid of the r squared. So v divided by r, and that's squared. That allows me to come in, and this r squared is going to get rid of that r squared. Now that we have that, we can simplify this and say it's going to be 1/2 times the mass of 0.5 times velocity squared, which is 10 squared. Looks just like the previous question, actually. So K rod is also equal to 25 joules. Now, if this wasn't a wheel, we would have had a different moment of inertia and a different value here.
Mr. Walkley,
Yes.
could you find the moment of inertia and then plug in the angular velocity from part A? You'd still get the same answer.
Yeah, it should work as long as we didn't make a mistake. Now, what if you made a mistake in A? You would be introducing that mistake into C. So that's your risk. If you're confident in what you're doing and you see that, absolutely. I have a nagging hesitance to use something that I calculated moments before, especially if it's on a quiz or a test. It's like, if I don't have to use that value, I'm not going to. Now, if it helps me, I'm going to, but I need to know that I've got confidence that I did that problem correctly. But yeah, absolutely, you should be able to use it. Also know too, that if we're rounding along the way, if in A, we had to round a lot, and now we're introducing that rounding down here, how much further are we getting from that desired answer? So that's just a couple of things that would float around in my mind as I'm doing it. But like you're saying, could we have just left the W there? Yeah, absolutely, we could. We had the radius. We didn't need to cancel out the radius. But if we didn't have the radius, it's good to remember the trick on how we would get rid of it. That's all. D is a real simple question. It just says, calculate the kinetic energy of the wheel. And you're like, wait, what? But it tells us by summing the two kinetic energies. So we're just going to say the total kinetic energy is equal to K plus K rot. I'm just writing it so we can see where it came from. And that's 25 joules plus 25 joules equals an easy 50 joules. Yes, it was that simple. It is that awesome. We are that awesome, right? It's not bad. It's easy, easy. Okay. We should be comfortable all the way through that point, kind of gave you a head start and walked you through each one. Kind of the attitude we need to take as we think things through so we don't jump in and get too nervous and too overwhelmed. So let's look at 5. I don't know what happened to 3 and 4. They must have not been any good. All right, we have a solid spherical marble. All right, so a spherical marble, we can just go ahead and say I is the 2/5 mr squared. Whether we need it or not, I like to get stuff in the margins so I can refer back to it. I've got mass is equal to 0.2 kilograms. The radius, a little bit. Yes, ma'am. A radius is equal to 0.05 meters. Let's see, set in a spring-loaded projectile launcher. Okay, so what this sounds like is like a pinball machine. You guys know, like legit pinball. You pull back the plunger, you're compressing the spring. Yeah, you got this. And you let go and since the marble going. So it's like that. So we've got, let's separate, since I have so many Ks going, I've got kinetic energy, I've got rotational kinetic energy. The K for the spring, I'm just going to list everything for the spring under this. So I've got my spring potential, and I'm just going to say for the spring potential, I've got K is equal to 1,000. There, and it's compressed. Now the compression of the spring we called X because that was the displacement of the spring when we compressed it. So we're going to say X is equal to 0.25 meters. And we want to calculate the velocity of the marble. So let me just mark that. The velocity of the marble immediately after it's launched. So we've got two situations, assuming it slides out without rolling and then without slipping. And it rolls here. Okay. So if it doesn't roll, we can say that when we pull the plunger back in that pinball machine, so no K-rot in the first part. Yes, correct. There's no K-rot in the first part because it doesn't roll. So when we pull back that plunger, right before we let go, what type of energy do we have right then?
Spring potential.
Spring potential. And then when that spring pushes the marble and is fully extended and the marble's off and going, we've converted that spring potential into
Normal kinetic energy.
Normal kinetic energy, translational kinetic energy, linear kinetic energy, call it Bob kinetic energy for all I care, as long as we know how to transfer it. We understand what's going on. I'm just kidding, don't call it Bob. All right, so we've got spring potentials becoming kinetic energy, right? So we have MGH is becoming 1/2 mv squared.
Mr. Watley, spring energy is not MGH. It's 1/2
Thank you.
squared.
Yes. Thank you. I'm trying my best to make people like say stuff. All right, so it's not MGH. It is potential, but it's spring potential. So tell me, what is it?
That's 1/2 kx squared.
Yes. Now, why is it my Wakeland student is talking over all my independent students? Come on, Knights. I got 2 Wakelands and 33 independents, and the person I hear the most is all the way on the other side of the tollway. Come on, y'all, represent your school. I'm not, hey, don't diminish, but the others step up. All right. Okay, so we've got this. Now, yes, 1/2 kx squared. So not all potential is gravitational potential. So don't go to sleep on me. Now, how many people wrote that down earlier when I wrote it down, MGH? They're just like, okay, it's MGH. All right, enough of that. Definitely not me. Good. I'm glad you didn't, but you got to speak up. All right, now I'm looking in the chat and I see where someone said MGH question mark. Yeah, you got to speak up. I'm trying to make sure you guys stay awake. I would not have let it go that far. All right, now that we're here, what's the best thing to do? What's the obvious thing to do to this equation?
Cancel the 1/2s.
Yeah. All right, so I like to cancel in red because it's something to go back and be able to see easily. So let's cancel those 1/2s. All right, and we're solving for velocity. So I want to get velocity by itself. So let's divide both sides by mass and then square root. That gets velocity by itself, right? So we've got kx squared divided by mass square rooted is equal to velocity. So if this was our exam in May, we're done. That would be an awesome position to be in, right? Because for the most part, we don't have to do math there. We just have to rearrange equations. And we've done that. We've solved for it. But they did give us some silly little numbers, so let's plug those things in. So we would have this square root of k is 1,000 times x squared. So 0.25 squared divided by m. M was 0.2. And that is our velocity. When I put this into my calculator, it's been a minute since I did it, but 17.68 is what I got, 17.68. And it would be in meters per second is our velocity, because we know velocity is in meters per second. So 17.68 meters per second is the linear velocity of our marble based on that spring sending it into action, ready to play our video game. I don't know,
Watley,
yes.
if it's rolling, why don't we include the rotational kinetic energy as well?
Here it's not rolling. It says the marble slides out of the launcher without rolling.
Right, okay.
But because you asked, let's do it with rolling. I'm just kidding. It's not because she asked. It's because B says it rolls without slipping. So we're going to say, okay, initially we're playing our pinball machine is on a sheet of the base of it, the bottom of it is ice. So it doesn't have any, it doesn't have a force in order to cause that rotation. There's no friction there. So it just straight slides. But now we're on a different machine, cheaper, more conventional machine where it has wood bottom. And now the marble comes through and it's going to be rolling. So we still start with spring potential. And now we've got both kinetic, because it's moving from point A to point B, but we also, because it's rolling, we're going to have K rod. All right, so we've got both going on here. And again, our spring potential is calculated by, what is it?
1/2
K squared.
Yes. 1/2 times K times X squared. Spread it out a little bit more on that one, is equal to 1/2 mv squared plus 1/2, what did we say it was, I omega squared. And we want to solve for velocity. And so it's probably going to be a good idea to, at least we can substitute our I for 2/5 mr squared. And then we can take our omega and change that to V over R squared in parentheses. So I want to kind of clean up, let me use my coloring. I want to clean up this part and incorporate the actual mass and convert things to velocity as much as possible. Because I want to solve for velocity, I want to narrow down the variables. And I don't have a number value for the angular velocity. I don't have a number value for my rotational inertia. So I need to convert them to something that I do have. Can we cancel out the halves? Yeah, you want to cancel out the halves right now? Let's do that. So let's cancel out that. Oh, not in black though. See if I can get it away. Oh, look at that. It cleaned up nice. All right, so let's cancel out the halves. That's a good idea. Let's get rid of that one, and that one. All right. And then let's go back to black, and we've got what? K times X squared is equal to mv squared plus, the I is 2/5, right? 2/5, is that what we said it was? Yeah, it is. All right, mr squared times V over R, which is squared. And then I'm gonna get my red pen back out. And this R square, we'll get rid of that R square. Go back to black. And essentially what I have is kx squared is equal to, I've got mv squared plus 2/5 mv squared. Once the r's cancel out, I have 1 mv squared plus 2/5 mv squared. That should add up to be 7/5 mv squared. 7/5 mv squared. Right, because they've got the same variables, 1 mv squared plus 2/5 mv squared. That works. Now that I have 7/5, I want to get the velocity by itself, right? So if I take the reciprocal of the 7/5 and do 5/7, multiply that on both sides, and then divide by m, that would sort of get me there. So let me draw an arrow and get this moved up over here where I've got more room. So if I did the reciprocal, I would have 5/7 kx squared is equal to mv squared. Divide both sides by m. That would give me what? 5kx squared divided by 7/5 m. And then if I square root it, that would equal to v. That would get me my v. All right, if I tripped along the way, you got to call me out. And then if I'm gonna do another arrow and say, come up here. Here's where I'm gonna put the actual numbers in. All right, I've got the square root of 5 times 1,000. Wasn't that my k? Yeah, it was. And then times x squared. What was my x? 0.25? 0.25 squared, all divided by 7 times mass. What was mass? 0.2. 0.2. When I put that into my calculator, I got 14.94. 14.94 meters per second. All right, now, if I didn't make a mistake, does my answer make sense? And it does, because I'm rotating, because some of that potential energy went into rotation, my velocity should have decreased. And it did. It went from 17.68 to 14.94. So the answers I'm getting are reasonable. Sort of makes sense. Should have some confidence in it. All right, if we're good with that one, it's a little bit challenging. Keeping up with the variables is a bit of a chore, but with some practice, we can do this. Let's take a look at, that's 5, A and B. There's no C and D to number 5. We're gonna do 6, A and B, and then I'm gonna hold off on C and D till the end of class. Otherwise, we end up running out of time, and that's just not a good thing. So let's scroll this up. Let's take a look at what we have for number 6, A and B. So we have a block of mass M slides up the incline. Okay, a little bit backwards from what we're used to. Usually we say, hey, a block's on the top, sitting up there, and it converts its potential to kinetic as it slides down, but this is reverse. We can handle it. Block of mass M slides up an incline shown above with an initial speed of V naught in the position shown. If the incline is frictionless, all right, it's got no friction, that's a gift. Determine the maximum height to which the block will rise in terms of the given quantities and appropriate constraints. A lot of fancy words, but
Mr. Watley, you read it wrong. It says constants, not.
what did I say?
You
Oh, I
said
said constraint.
constraints.
See, I'm blind, deaf, and dumb. So you just got to deal with it. Yeah, I read, my eyes move faster than my mouth does, and I'm wearing contacts, so I can only see somewhat. All right, appropriate constants. What type of energy are we starting with?
Kinetic energy.
Gravitational potential.
Oh, what are you saying, gravitation? We're on the ground.
Oh,
Kinetic energy. Yeah, we're on the ground and we're moving up. Now, normally we do start with gravitational potential, but now we're on the ground and we're moving on up. Okay, so we're starting with kinetic energy. And then as that kinetic energy, it gives us velocity, but as we go up the hill, that velocity is going to decrease so that we can gain height. This is like the roller coaster. You're on the Texas Giant and you've gone all the way down to the bottom and you're flying down really fast and you start to go up the next hill. That velocity is going to give you height, so that kinetic energy becomes gravitational potential. And I can say with confidence that it's 1/2 mv squared is equal to mgh. And this time I mean it. Now I can get my red pen out and I can mark out mass, because mass is on both sides. Mass doesn't matter, it cancels out. I'm left with 1/2 v squared is equal to gh. I want to solve for height. All I got to do is divide both sides by g, right? So it would be, I'm going to come up to the other side just because I feel like I'm going to run out of room. I would have v squared divided by 2g is equal to height. Isn't that beautifully simple? Wish they were all like that. All we had to do is rearrange
Mr. Watley,
square. Yes, sir.
you should put VO squared because that's what they gave you. They didn't give you a V. So there you go.
See, you're going to take me from feeling really good about a class to being like, man, I need to do a better job. No, thank you. Keep me straight, because if I drop something or if someone's confused, I don't want them to be confused. So yeah, keep me on my toes. Keep paying attention. Let's look at B. because B, now we've got friction. Same problem, but we've got friction that's going to steal some of our energy. We've got a complete conversion of energy from kinetic to gravitational potential until there's friction. K-rot doesn't come back because we're not going to rotate. We're not going to rotate. The box isn't going to rotate, but it's kind of like this. You ever go to the park when you're a kid and you slide down one slide and boom, really fast. At the bottom of the slide, you hit the ground running, you're going so fast. Then you go back to that park and now it's wintertime and you're wearing jeans and you go to slide down the slide and you go halfway down and you're like having to scoot to like get to the bottom because friction, right? So friction is taking some of our energy. So we're going to say we're starting with kinetic energy, and when we end, it's going to be gravitational potential plus friction. Okay. There's a couple of things we need to do for our setup first, though. All right. I need to gather some intel. All right. We need to go back to our unit on forces and say, okay, what does this look like? Well, this mass is sitting on this incline. If I were to just draw gravity coming off of it, it would be straight down, FG. All right. Now, if you were with us in my class before, you're going to be used to seeing me draw gravity sideways, which is weird for some, but I like to see vertical and horizontal forces pointed vertically and horizontal. What I mean by that is I'm going to take that mass and I'm going to turn it clockwise just so that it looks like this. I'm sorry, this is the only way I can see it. This is how I visualize it. Well, if I turn it like that, my force of gravity arrow now, my mg is going off that way. Okay, yeah, I'm sorry. It's going to weird some people out that haven't seen me do that before, but it's just, it is what it is. It's really cool. I get to run the zoom so I can draw it which way I want to. That means I've got a component of gravity that is vertical, and I've got a component of gravity that is horizontal. That's why I like to do it like that. It allows me to see the vertical component of gravity and the horizontal, and I can see it up and down and sideways. It's a way that I visualize it, and I can't get away from it. The vertical component of gravity, that is right next to my angle theta. And so if it's adjacent to it, we're going to say that that is mg cosine theta, right? And then the component that's horizontal, that's on the opposite side. Sine uses opposite, I'm pretty sure, which would make that mg sine of theta. All right, if I forgot this and doing it wrong, somebody's got to speak up, but it seems like today you guys are willing to, which is freaking awesome. I had somebody watch a recording in the from my face-to-face class, and they're like, there's only 2 people that talk. It's like, well, I got to encourage them more, I guess. Going up is my force normal. My object is not accelerating vertically. Horizontally, side to side, yes. Vertically, no. So my force normal is equal to the force that's balanced to it in the vertical. So force normal is also mg cosine of theta. And then my friction is going this way. And my friction is going to be force of friction is equal to the coefficient times mg cosine theta. Because force of friction is basically coefficient of friction times force normal. And it has—
Mr. Wiley, don't you mean sine theta instead of cosine theta because it's going in the same direction as sine theta?
No, because it's force normal.
Oh, okay.
Coefficient.
Multiplied by the, okay.
Yeah. It's if we go like a throwback for, hey, for those that are wondering, remember force friction is fun where it looks like this. So force friction is fun, F-U-N. So we take whatever our force normal is and multiply that by coefficient. And yeah, my writing is kind of small too. So let's see if I can blow it up just a touch. So I have force of friction is equal to coefficient times mg cosine theta, because it's force normal times coefficient. So we at least have identified what my force normal is, or not my force normal, then subsequently my force friction. So let's go back to B and let's start to build our equation. It's a process, but drawing the free body diagram, it helps. Now we're still starting with kinetic energy. Okay. This is still a box. It's not rotating. It's still a box, a crate, a mass, whatever you want to call it. What do they call it? A block. All right, it's a block. And then as it goes up, yes, it will get some gravitational potential, but we're going to lose some energy to friction. Now I'm going to put the force of friction. but I can't leave it just as the force of friction because this is an energy equation. The force of friction is not energy. How can I make the force of friction energy?
You multiply by the distance, so d, or a distance.
Yes. Why? Tell them why.
Because
Force times
work is the change in energy, so the amount of energy that's lost due to friction is work due to friction, which is just force times distance.
Yeah. If you remember, work is force times a displacement or a distance, right? Force times distance. We've got a force. If we do a force times a distance, that's work. What's the unit of work? Joules. What's the unit of energy? Joules. All right, so now we need to incorporate a distance. Let's go back up to our picture. Let's draw it, okay? I'm gonna use my own drawings because I don't know why. It's just because I've done it so many times now that I'm just gonna continue to do it. All right, there is our incline. This is our angle theta. All right, this is the height over here on the right. That's what we ultimately want to solve for, is the height, right? Well, the mass is going to be going up this incline. Let's say it's going up the incline a distance of L for the length. All right, it's going to go up L. So when we go back to our formula, we're going to say it's force times L, because that force of friction times the distance is how we're going to calculate the energy that's lost to friction. Now, L was not a listed variable that we're allowed to use. So let's go back to our picture. We're allowed to use height. We're not allowed to use L. So how would we solve, what can we use to solve for L but incorporate something other than L? How do we solve for L here?
Oh, it's a right triangle. You can use trig.
Tell me, what do you want to use specifically?
Sine theta is h over L.
Yeah, let's start. So earlier today, somebody even said Pythagoras, and I was like, hey, slow down because I've got two sides and an angle. But right, we want to use trig here, and we want to say, all right, you told me sine of theta is equal to h over L, which is the opposite over the hypotenuse. If I want to solve this for L, I would say that L equals what?
H over sine theta.
Yeah, absolutely right. H over sine theta. Okay, so we know that the length that the box is going to travel is equal to h over the sine of theta. I'm allowed to use h and I'm allowed to use theta. Okay, perfect. Let's scroll this down. Let's see, do we want to rewrite this with that, or no, let's start defining our variable, our equations now. So kinetic energy is still 1/2 mv squared is equal to gravitational potential, which is still mgh, plus the friction. And we said, I got to scroll up to see my friction. We have mu, that's an ugly mu, times mg sine theta. And then I've got to multiply that by L, and we
Sure.
said L.
mg
Yes?
cos theta.
What's that?
It's mg
Oh,
cos.
yeah, you're right. Cosine. Good job. Oh, that still looks like a freaking S, doesn't it? Like SOS. Cosine theta. All right, now tell me what my L is. What am I putting in for L?
H over sine theta.
Sine theta. Got it. All right. Is that right? Y'all check it. Make sure it's right. I've got kinetic energy is equal to gravitational potential plus friction times the length that friction is going to be applied for. Okay, looks a little messy, but we can clean it up a touch and we can just rearrange to solve for velocity, right? Oh, no, not velocity, height. We're solving for height. Okay, so how can I clean this up? What's something I can do?
Can't we cross out
Divide by
the
mass.
Yeah, all right, so were you both saying mass?
Yes, mass.
All right, mass, mass, mass. All right, I want to do this next step, and it was controversial earlier today, and that is I hate the half. I just hate the half. I don't like fractions. I must have not gotten along with my teacher that taught fractions in whatever grade that was. I really terribly want to multiply both sides by 2 just to get rid of the half. So I'm going to do that. Now, if you want to start to move things around in your own way, that is totally fine. There's more than one way to simplify as long as we get to the right end component. I'm going to get rid of the half. It's just like one of those things, like some people have to have their shoes perfectly lined up, weird little ticks about you. I got to get rid of that. Do we multiply force of friction by length to get the energy used for distance? Yes, because friction is going to use some energy, and the only way to get a force into an energy equation is a force times the distance it was applied makes it energy. So yes, that's why we do that. Could you please explain why you put L in the equation again? Okay, I hope, let's see. Okay, I hope I'm answering for both of you. So the reason we have L in the equation is that's an energy equation. And we started with a certain amount of energy, and then that energy was broken into 2 other types of energy. Energy taken by friction and energy that was converted into height, also known as gravitational potential. Now, we can't say it's gravitational potential plus friction because friction's a force. We have to make it an energy, and force times a distance is work, which is a change of energy. And that's why we had to incorporate L. I hope that helps. I hope that helps. But you can't just put force into an energy equation and say, ta-da. You have to make it energy because it's an energy equation. Okay, perfect. All right, so what I did is I multiply both sides by 2 because I hate the fractions. So let me see what I end up with that. So I'm going to have v squared, and some of those students really did not like that. All right, 2gh plus 2 coefficient g cosine theta. Actually, you know what? Let's be a little bit more controversial. I'm going to take out cosine. I'm going to switch the cosine and the h just because I like those together. So I'm going to bring my h down times h times cosine of theta over the sine of theta. You're still, the order that you multiply stuff doesn't matter. It doesn't change it. 2 times 3 times 4 is same as 2 times 4 times 3. So I like to keep the cosine and the sine together because I kind of know which direction this is going. So I just move the h over and the cosine over. I just flip their 2 positions. All right, it shouldn't be terrible of me. Now that I have this, the next step I want to do is divide both sides by h. I want to move the h to the left side. It's just my preference. Yes, there's more than one way to do it. But if I divide both sides by h, what I end up with, I'm going to try to fit one more line before I have to go up to the next side. So I would have v squared divided by h is equal to 2g plus 2 coefficient g times cosine of theta divided by sine of theta. All right, I think I'm still okay. And now I'm going to draw an arrow to say, hey, bring this up and over here. If I divide both sides by v squared, I would have 1 over h on the left side is equal to 2g plus 2 coefficient g times the cosine of theta divided by, and I would have v squared times the sine of theta. Well, I don't want 1 over h. I want to flip it. I want to get the reciprocal. I want h over 1. Let's see.
Mr. Watley,
Yes.
you can't do 2g plus 2 mu g times cos theta over sine theta because the 2g wasn't part of the first expression.
So, wait, what?
The cos theta over sine theta only applies to the second half of the v square expression that you had before.
Oh, okay. You want me to just keep them on top? Like this? Like that?
Yeah.
Okay, I'm okay with that. I wasn't really looking at it. I was just kind of writing it out. But I'm okay with that. All right, so now I just need to do the reciprocal.
Mr. Watley,
Yes.
you can convert cosine theta over sine theta to just cotangent theta if you don't want
Yes.
fraction on a fraction.
Yes, but I've got to flip it still. So when I flip it, what would it be?
Tangent.
Tangent theta.
Right. So that I was going to keep it like that. I didn't want to convert it to cotangent and then tangent. I just wanted to flip it and then make it tangent. All right. So when I flip it, what would it be? All right. So, okay, here, I'll tell you what, let's walk this through. So you're saying this right here is essentially cotangent, right? Do I just write that as COT? Is that okay? All right. I don't want to upset anybody that's like,
Yes,
hardcore math.
that's how you write it.
Well, I want to make sure I'm not going to like anybody's hardcore math is like, no. All right. So then if I do it that way, I've got the cotangent, right? And then I need to flip this. So then am I still in my, yeah, I'm still in black. All right. So I need H. And then when I flip this, I'm going to have V square on top, right? And then what do I have?
Well, if it depends, if you keep the angle thingy on top, it'll become tangent, but if you move it to the bottom, it'll still be cotangent.
Is that okay?
Yeah.
Let's leave it like that then.
Okay.
It's a little bit crazy with the variables. There's more than one way to get there. Let's see. Can we change H sine theta into H times? Since it makes it easier. Yeah, if it makes it easier to separate H, yes, you can. Let's see, or is what you do change cosine theta. It, Darshan, for your question, it really depends on what you're comfortable with. So if you can see it, you're going to be fine. If you write it out that way, you're going to be fine because the graders will understand it. If you're looking at multiple choice, you'll just have to make a comparison, and it's not going to be like picking between making small errors or making small changes that are equivalent to each other. So you're going to be okay. Cotangent is just simply cosine over sine. That's all cotangent. It's an abbreviation for cosine divided by. It's the same thing as cosine over sine. For the person that asked for what's cotangent, it's a lot cleaner to write cotangent than to write cosine over sine. That's for sure. Okay, now that that's there, I do want to leave C and D for you to attempt. They're not even as challenging as B, in my opinion. I think B is probably the hardest one on the page, but C and D will give you good experience. I do have the solutions for it. I'll post it later this week once you've had an opportunity to kind of struggle through it, make your attempts and work through it. Then you'll be in a better position to then kind of see what the answer is. What we want to do right now is switch over and take some notes on angular momentum. So we've been practicing what we've already learned, but we need to get into new material. So let's start with that, or let's get that started at least. So angular or rotational momentum is going to be similar to what we've already learned as far as our linear momentum. If we remember linear momentum, we said momentum before is equal to momentum after. And momentum is simply mass in motion. So we take, if we have two masses, all right, so we've got mass one, mass two, and let's say it's mass one, we've got 2 kilograms. And it's going to be moving at 5 meters per second. It's coming up behind another mass, let's call this 6 kilograms, and it's moving at 3 meters per second. They're both moving to the right. Okay, so a collision is going to happen because the one that's on the left is going to overtake or attempt to overtake the one on the right, and it's just going to slide into it and they're going to stick. Let's say they stick together. So then collision occurs. Now we've got one big mass. That's the 2 and that's the 6, still kilograms. And then they're going to move together at some velocity, and that's what we're looking for. What is that velocity? And we know that momentum is conserved. Conservation of momentum before is equal to momentum after. And momentum is, let's see, P is equal to M times V. Initial momentum is equal to final momentum, if we want to say I and P, the the PI, that's initial momentum, the PF, final momentum, just kind of getting that stuff out there. Hey, we know that's what's going on. So when we had to calculate it before, we would say M1 V1 plus M2 V2 is equal to the quantity M1 plus M2 times V. And we're solving for V, okay? We would have what? Essentially 2 times 5 plus 6 times 3 is equal to 8. Did I do the right numbers? Yeah, I did, right? Yeah, okay. 8 times V. So 10 plus 18 is equal to 8V. 28 is equal to 8V. Then 28 divided by 8 equals the velocity. And I really don't care to clean it up any further than that because it doesn't really matter. This is just an example of that was our linear momentum. We knew it was conserved. We know it's mass times velocity. It's mass in motion. If you're not moving, you don't have momentum. But you're going to take all the components from before, their momentum, and make it equal to after. Now, a mistake I saw in the momentum test is we had the urge to add up the masses and then add up the velocities and multiply those two numbers. You don't say on the left side, 2 plus 6 is 8, 5 plus 3 is 8, so the momentum is 8 times 8, 64. No. Mass times its velocity plus mass times another velocity plus mass, however many you have, adding those up. Okay, so let's select this. Oh, the second momentum equation I wrote, this one right here, that's just saying the initial momentum is equal to the final momentum. That's all that's saying.
Mr. Watley,
Yes.
this was a perfectly inelastic collision, right?
Yeah, they stuck together. It's inelastic. Yeah. And again, this is only supposed to be a reminder of saying, hey, the momentum before is equal to the momentum after. You know, no reason to be overwhelmed by it because I'll underwhelm you pretty quickly as far as angular momentum. So let's just select this. I'm just going to clear this out so we've got room to actually do angular momentum. So we remember what momentum is. We're like, cool, we took a test on that. So wish we could go back to that stuff because that was back when life was easy. It wasn't easy back then, but hey, we feel like it was. So momentum, just like P was our linear momentum, we've got to choose a really weird letter for our angular momentum, and L was the winner. So L is our angular momentum, and that's equal to our rotational inertia times our angular velocity. That's how we calculate it. And we can say that the initial momentum, angular momentum, is equal to the final angular momentum. Whatever you have before the collision is what you're going to have after. This is assuming that we don't have any external net torques causing some sort of change in the angular velocity. This is assuming that something is allowed to rotate, like there's not something that's rotating, but then, you know, something's going to come along and be like a doorstop and just like keep it from moving. Okay, it's got to be free to rotate. There can't be any gremlins along the way making changes. All right. That being said, are we okay with this? Are we okay to say our initial momentum is equal to our final, our initial angular momentum is equal to our final? Because I've got an example that I kind of want to bring up. And let's say we've got a windmill, and I can't draw a windmill, but there's the ground. And then I've got, like, there's a fin to the windmill. Here's a fin to the windmill. There's a fin. There's a fin. There's my windmill. Okay. And let's say it's right alongside the building because the school wants to say, all right, this is, let's call it Frisco High, since none of us are from Frisco High. There's Frisco High School. And they want to represent the community and say, hey, we've got clean energy, renewable energy. You know, we're not using whatever. Now the windmill's not moving. What's my angular momentum?
0. It's not
0.
moving. It
Very
doesn't.
skeptically, yeah, it's not moving. And very skeptically, he said 0. All right. Now, what if we have a freshman standing at the top of a building, and the freshman has big old chunks of mud. And he wants to throw it at the windmill. And when he throws it at the windmill, so here goes the mud, it's going down. And here it is, it's about to hit the windmill. Now it hasn't hit the windmill yet. And so we're like, okay, well, there's no angular momentum because nothing's rotating. There is no angular velocity. And Whatley said it's I times omega, and omega is angular velocity. And if it's not rotating, there's no angular velocity, so there's no momentum. But then that's before the collision, all right? After the collision, this mud sticks onto this fin, and then this system, because it hits it, begins to rotate. Well, if it rotates, it's got angular momentum. So how do we justify that? And this is kind of a rhetorical question because it's, I haven't provided you the keys to understand where did the angular momentum come from, but it had to have existed because it's a hardline rule. Momentum before is equal to momentum after. There had to have been momentum, had to have been. And the way that we reason this out, sort of like a little of a,
I think
Go
it's
ahead.
because mud. I think it's because the mud pushed the windmill down, and that started the rotation.
right. I mean, you're
Okay.
absolutely right. But where did it's going to be, how do we account for the angular momentum before the mud hits the windmill? How do we account for that? That's what we need to incorporate. So let's say this, we've got a point mass. Let me make sure, let's go back to black. All right, we've got a mass. Here's our point mass right there. And it's moving to the right. So it's got velocity to the right. Okay, and I'm gonna do like dot, 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 dot. It would keep going to the right, and this is its line of action. All right, that's a term we've used a little bit lately, right? Action. There's our line of action. And now we've got, let's say this is our pivot right here. There's our pivot. And so it might have something that comes up just like the windmill. You know, okay, we get the idea. We've got something that pivots. And if we've got a mass that its line of action, I'm talking about initial. Uh-oh, I think I'm behind on the chat now. Let me just take a quick look. Can you explain it was 0, that's what I'm. Okay, let me, yeah, I think it's kind of, all right, let's look at this. Now, if we've got a mass with a velocity, it's moving in a straight line, and it can interact with something that's going to rotate, we're going to say that mass does have angular momentum. And the way that we calculate that angular momentum, it's going to be equal to the mass times the velocity times the radius from the point at which that object is at 90 degrees, its line of action is 90 degrees to the pivot. So from this point to here, that's our R. This MVR is angular momentum originating from an object moving in a straight line. So in the case of our mud going down towards the windmill, its velocity right before it hits the fin of the, what I call that, windmill, all right? That right before it hits the fin, it has mass, it has velocity, and it has a radius to that pivot point. So it has angular momentum, and that angular momentum is converted all the way to the windmill. In this case, when it's completely converted, we would say that the initial momentum is equal to MVR. The final momentum is equal to the rotational inertia of the windmill times the angular velocity of the windmill.
Mr. Watley,
Yes.
the chunk of mud is dropped straight down. So how would it have angular momentum if it's traveling straight down in a straight line?
Look at my, let me refer you back to the right side of the page right there. Because a mass that's going in a straight line that interacts with something that will rotate has angular momentum. Let's call it potential momentum if you prefer. It has the potential to cause something to rotate, therefore it has it. It's
Okay.
weird. It's, you know what it's kind of like? It's like
It's
physics.
because it hits the thing at a 90-degree angle. So
Yeah, when you use the radius from that 90-degree angle. But it's sort of like physicists were sitting around one day and say, man, here's an exception. And they're like, well, we got to assign it somewhere. And this is where they put it. Okay, that's not true, but it feels like that sometimes. Now, in this instance, that chunk of mud going straight down, because it has a radius, it has a distance from a pivot point and hits something to make it rotate, it has angular momentum because it's going to transfer some of that energy to the angular momentum. Now, let's say that instead of mud, the mud dried and we're just dropping dirt, and dirt's not going to stick. It's going to hit, let's say it's a concrete block. It's going to hit the wing of the windmill, but it's not going to stick to it. Okay. If that happens, what we would have to say is, I'm going to erase what's here because I've got to change it and I don't want to confuse anybody. In this case, I want to erase this. And then I'm going to add in my drawing. I'm going to show the mud continues down. All right, it hit it. It caused it to rotate, but the concrete block is still heading towards the ground. So here, what I would say is my initial angular momentum is simply mass times initial velocity times the radius, mv not r, okay? My final momentum is still rotational inertia times angular velocity plus m final velocity r. So the concrete block, forget about gravity speeding it up. Let's just talk about, hey, it's falling. When it hits the windmill, the concrete block itself is going to transfer some of that velocity, some of that energy to the windmill, causing to rotate, and the block itself will slow down because of that impact. So we started out with mass, initial velocity, radius, and we finished with the rotational inertia times angular velocity, plus that block still is moving, so it still has some MVR going for it. It could potentially hit something else. So here we would be able to say, if we put it together, we know that L naught is equal to L. So then we would say mv naught r is equal to I omega plus mvr. Provided certain pieces of information, we could solve for other pieces of information. The question asked to me is, if the dirt wasn't moving in a straight line in a 90-degree angle to the windmill, would the equation be the same? The good thing is the windmill is a circle. So no matter what direction that the rock is coming at, we can reorient our picture until it is at a 90 degrees, because as it comes in, whether it's coming in like this, I'm guessing you can see me. If it's coming in like this or it's coming in like this, whenever it's interacting with it, it's at a 90 degree to the pivot. We can orient it to where it's at a 90 degree to the pivot. If it's coming, let's see if it's coming in like this. Oh no, that might not be true. If it's coming at a different angle. What we're looking at is, okay, this is what you would do. Draw your line of action all the way through, and your line of action will always be 90 degrees to the pivot. It may not hit it, but let's say it's coming at an angle. Let me use purple. Let's say it's coming in like this, right? So yes, it's not hitting the fin at 90 degrees, but its line of action is going through like this. So then we would measure it when it's 90 degrees to the pivot. How far is it from it? When would it be 90 degrees? Gosh, I want to draw it like here. There's my perpendicular. Your MVR is your mass times your velocity times the radius. And the radius is based on the line of action when it's 90 degrees to the pivot. And then it has to be moving in a straight line. It can't be thrown like a baseball where it's like, hey, it's coming in a curveball, and just zigzagging through. It can't be like that. I mean, it's going to be coming in a straight line. At least for AP1, it's coming at a straight line. We don't have like baseball and softball pitchers coming out there and throwing things at weird angles. All right, that's my notes. I want to go to the notes page. There, let's see. Is the image in red turned 90 degrees? Okay, hang on a second. Let me take off my purple when I was just kind of talking through something. So my image in red is at 90 degrees, right? Still on the erase, dang it. Right here, that's the 90 degrees because it's above it. It's directly above it. It's going, the line of action is perfectly horizontal, and then a vertical line from the pivot up is your 90 degrees. So that one I'm using, yeah, it's basically turned 90 degrees from the original picture. So my windmill from Frisco High School was being dropped vertically. My picture to the right is a horizontal example. The horizontal example is easier to work with because we don't start questioning things like, well, you've got gravity accelerating and all that. It's like, okay, I want to set that part aside to just focus on is the velocity at impact when we're at 90 degrees. What is my velocity at impact? Draw the line of action. It's 90 degrees from pivot to line of action. Now, don't get too hung up on it because most of these questions are going to be pretty direct. So it's not going to be how you have to draw it and then make a lot of assumptions because you're really not. Let's go to the notes page that is kind of a default note page. Let it load up.
Could you go back to that page for a quick second? I forgot to take a picture of that thing. All right, thank you.
Oh man, I'm drawing with my fingers now. Let's see.
Oh, Mr. Watley,
Yes.
for the previous picture, does the line of action not need to be parallel to, I guess, like the windmill part that's being hit?
No, the line of action is a straight line of where my particle or my mass is moving.
Okay.
So it's like remove all things in the world, and it's like, where is that particle moving? That's its line of action. And then we're going to look at when is it perpendicular to the pivot and how far is it from the pivot at that point.
Okay, thank you.
When you go to the notes page, this is what's in Canvas. It gives you a quick reminder of linear momentum and kind of the conversions to angular momentum. No big mysteries here. There's 2 sample problems I want to hit on, but we've only got like 7 minutes of class. So I'm going to try to do these with a little bit of pace. That way you can see them. You'll have reference to them in the recording if you need that. But what I would like for you to do is to finish number 6 on that previous page on the rotation and the second page of this one. So this goes into a second page and there's 2 sample problems on the back. I want to do the 2 sample problems on the front just to give you some reference and kind of see like, hey, these problems aren't as bad as what they seem they might be. So let's take a look at this real quick and see if we can clip through it and beat the bell, basically. We have, what is the angular momentum about the axle of a 500-gram rotating rod? Okay, well, 500 grams, that means mass is equal to 0.5 kilograms when I make the conversion, right? It tells us that it's an axle that's rotating at the center. So I know I is equal to, it's 1/12, right? 1/12 mr squared. All right, what else do we know? We know that it's not mr squared, it's ml squared. Sorry, let me fix that. I'm just so used to doing mr squared today, I want to make everything mr squared. So I've got 1/12 ml squared. What else piece of information do I need from this? I see that L is equal to 2 meters. And then from the picture, I can see that it says 120 RPMs. So 120 revolutions per minute. And I'm going to convert this. I know that 1 revolution is 2 pi radians. And I know that 1 minute is 60 seconds. Put minutes there. All right, so the minutes cancel out. The revolutions cancel out. So I've got 120 times 2 times pi divided by 60. When I did that, I got 12.56. 12.56, and my remaining units are the radians per second. Radians per second. And I know that omega is 12.56 radians per second. Just based on the unit tells me what the variable is. Now the question asks, what is the angular momentum? All right, well, we know that angular momentum, L, is equal to I omega. Okay, cool. We can do this. L is equal to I, we said is 1/12 times m times L squared, and then times omega. All right, which equals 1/12 times m is the mass, 0.5, times L, which is 2, it's squared, times omega, which is 12.56. I put that into my calculator and I got 2.09. 2.09. Here the units are going to be kilogram, meters, square, seconds. Now, I don't expect you to memorize the units, especially this one. The other units that we use a lot, yes, know those. It helps you with the problems. Here, the only reason I know the units is because it told me. I see it up here at the top, actually, when I go up here. All right, so pretty straightforward. Most of these questions are. The next one has kind of a fun twist to it, so I want to work number 2 with you. Here we have a rubber stopper rotates in a horizontal circle with an unknown angular speed. If the stopper revolves at 64 radians per second, after the radius is reduced to half of its initial value. So we're going to reduce the radius to get to that. And we're looking for the initial value. What is the angular speed of the stopper? Okay, so what we know is that the summation of our momentum, or at least our initial momentum, is equal to our final momentum, right? We know that. Our initial momentum would be like our initial, our moment of inertia, our initial moment of inertia, times our initial angular velocity is equal to our final times our final. I'm not trying to be cryptic with this. I'm just saying the before is equal to the after. The initial is equal to the final. Now we're solving for our initial angular velocity, right? So I'm just going to divide it over and I'm going to say, well, omega naught is equal to I omega over I naught. Fair so far? Just rearranged to solve for the thing that we're looking for. Now I want to kind of break apart the rotational inertia into what it is. Okay, and they gave me a definition up here in the problem. They said I is equal to mr squared. So here I can say that omega naught is equal to, all right, I is mr squared times omega over m. Now here I'm going to say it's r naught squared because it's my initial angular momentum based on my initial radius. Okay. Now the mass didn't change, the radius did. So let me get my red pen out and I can cancel the masses. That's pretty straightforward. When I do that, let me give myself some room. Let me come back up here and work up here. I've got omega naught is equal to final radius squared times final angular velocity divided by initial radius squared. All right, where can I go with this? They told me what the final angular velocity was, but they didn't tell me anything about what the size of the radius is. What can I do with this?
The problem tells you that the original radius was 2 times that of the final radius, so you can substitute the value in.
Yeah, so like final radius is equal to 1/2 original radius, right? So I could do it and say, all right, well, 1/2 r naught squared times omega over r naught squared is what omega naught is. Okay, I'm buying that because this r naught squared takes out that r naught squared. And then I can say, okay, omega naught is equal to 1/2 squared times omega. Omega naught is equal to 1/4, not 1/2, hang on. 1/4 times, what they say omega was, 64? So that means omega naught is, what's 1/4 of 64? 16? 16 radians per second. So learning the concept is, struggle on the first day a little bit, but we can see how the practice problems work. We set momentum before equal to momentum after, and then we just kind of go to work. We substitute the things that we can, and we solve for the variables that they ask us to based on the information given. All right, so they're going to dismiss here and